tertiary acyl halide, and it's going to react with a polar solvent like ethanol, maybe water, maybe methanol. And we're going to get a substitution product or an elimination product, sometimes both. These are going to be stepwise processes, so they don't occur in a concerted fashion. That's what makes them different from the SN2 and the E2 reactions that we studied previously. The rate for all of these is going to be equal to the rate constant times the concentration of the substrate. So the amount of the reagent here, the water, the ethanol, the methanol, is going to be irrelevant. So first we'll look at the SN1. The first thing that's going to happen is the loss of a leaving group, followed by a nucleophilic attack, and then frequently we're going to have a proton transfer. Let me move this up so we have a little bit of space, and I'll show you an example. So we have to start with something that's tertiary. There we go. It's a tertiary halide. So the very first thing that's going to happen is the leaving group's going to leave. So the protons, the electrons that are attaching the bromine to the carbon go with the bromine, and that's going to give us a carbocation and also a negatively charged bromine. Okay, that's the first step, loss of a leaving group. Then we'll have a nucleophilic attack. So let's make it blue is a nice color. Here's our ethanol molecule. And some hungry electrons here are going to attack the carbocation. They attack this carbon right there. Okay? And we get leave myself plenty of room, and this comes down here. The oxygen is the one attached. We've got, and it's of course positively charged because an oxygen with three bonds is positive. Then we'll have a proton transfer, and I should have done a better job of writing my electrons there. So we'll have a different ethanol, or maybe water, and it will come along. These electrons will attack and steal that proton. The electrons that are between will go to the water, to the oxygen there. And we end up with our product. In 3 steps. So it's first, we have first order kinetics. The rate is only dependent on the substrate. And this is what we would expect the reaction diagram to look like. We'll start down here. I'll have kind of a big hump, and then another hump, and then a third hump. At the top of each one of these is the transition state, and the intermediates are on the low spots. So we start with our tertiary here. We have the loss of a leaving group here, and we end up with our carbocation, a reaction intermediate in the valley. Then we have a nucleophilic attack, and we get our second reaction intermediary. And then finally, with proton transfer. So change that. Our proton transfer. And we end up with our final product. So an E2 reaction is in two steps. First, we'll have the loss of a leaving group and then a proton transfer. So if we and we'll just have an X for our halogen this time. First thing that's going to happen is the halogen leaves. And it takes its electrons and it goes home. And this is left as a carbocation. The next step involves the hydrogens that's already there. A base is going to come along and steal just the proton. The electrons that are connecting the hydrogen to that carbon then will go here and that'll give us a double bond. So we'll end up with, and let me get the right color. There. All right. This will be an elimination. And it is unimolecular, which is why we call it an E1 reaction. So first, let's draw the carbocation intermediates that are expected when these compounds ionize. What's going to happen here is that this bromine is going to take its electrons and leave. So we'll end up with and the chlorine is going to take its electrons and leave, so we'll end up with, I'll give my drawings here, but the carbocation intermediate will be right there. The bromine takes its electrons and leaves. This gives us now, for this one, we have a resonance structure because we've got a double bond that's allylic to a positive charge. So these electrons will be drawn to here, and we'll get we get everything drawn. Double bond, new double bond here, and this will be a carbocation. These are resonance structures, not a reaction mechanism. So let's see what happens with F. The iodine takes its electrons and leaves, and that leaves a carbocation here. It's allylic to this ring, so we'll get electrons that will travel, and we'll get a double bond here, and these double bonds are not changed, and the carbocation is now on this carbon. These bonds will travel all around, and we'll get a series of resonance structures here. Carbocation will be there. And then lastly, we'll get a structure, that goes all the way to there. And the last structure will look something like this. These are all just resonance structures. Double bond. This one is unchanged, and this one is down here now, and that leaves our carbocation.